Hello, Honors Chemistry students. This is Mr. Spurk, and this is your Chapter 5, Section 2 notes, Electron Arrangement in Atoms. Excuse me. So, what we're looking at here is an electron configurations in the periodic table. So you're going to have one of these charts on the activities we're going to do in class, and what I want you to notice is the different colors. So you have this light blue region, a green region, this orange space, and then the purple. So notice that over here we have all the s orbitals that we briefly talked about in section 1. After the s, we go to the p, then we have the d, and then the f. Now what I want you to notice is that the 1s is for hydrogen, and as we go across the row, we swing back, down, and around, and go through as they increase. So we have 1s, 1, 1s, 2, 2s1, 2s2. Then we go 2p1, 2p2. So just like the periodic table goes in order of increasing atomic number, we're going to follow that pattern as we go through the electron configurations. So keep that in mind as we talk about this set of notes. So an electron configuration is the way in which electrons are arranged in various orbitals around the nuclei of atoms. And we know we talked about the dumbbell shape, the spherical shape, the flowers. So electron configurations are a way for us to represent those. There are 3 rules when it comes to electron configurations, and they are the Aufbau Principle, the Pauli Exclusion Principle, and HUDs Rule. These are all named after the scientists who discovered them. So we're going to talk about the Aufbau Principle first, and this is, the Aufbau Principle states that electrons occupy the orbitals of lowest energy first. In the Aufbau diagram, each box represents an atomic orbital. So again, look down to the bottom and notice that energy increases as we go up. So we start at the bottom. So we have to fill in starting with the 1s. Then we would go to 2s, 2p, 3s, 3p, 4s, 3d, then 4p. So we start at the lowest energy and then work towards higher energy. This is the Aufbau Principle. So the Aufbau Principle shows the relative energy levels of the various atomic orbitals. So again, it starts at low energy and they increase in energy as we get higher. And the range of energy levels within a principal energy level can overlap the energy levels of another principal energy level. So what that means is, remember, principal energy levels are 1, 2, 3, and 4. And then we have the energy levels or the sublevels that are the S, P, and the D. So notice here we have some overlap. The 3D overlaps the 4S and the 4P. So that's going to be important for us as we move forward. So the 4S is actually lower in energy than the 3D orbital, even though it is a part of the third principal energy level. The next rule was the Pauli Exclusion Principle. The Pauli Exclusion Principle states that an atomic orbital may describe at most 2 electrons, and 2 electrons within the same orbital must have opposite spins. So a spin is a quantum mechanical property of an electron and may be thought of as counterclockwise or clockwise. We use vertical arrows to indicate electrons and its direction of spin. So when we draw an orbital, we'll typically see them as a box or maybe just a line. And the way we would represent those electrons is this first electron has an up spin, so we represent that with a half arrowhead, and then it gets paired with a down spin, so a clockwise and a counterclockwise. So again, if we use the line orbital representation, just like this. So within an orbital, you can only have up to 2. 1 is okay, and 2 is the max. A little easy tip if you want to write off to the side to remember that the Pauli Exclusion Principle is about opposite spins and 2 electrons is to write the word Pauli like this. So there you go. Pauli exclusion principle tells us about it describes two electrons and they must have opposite spins. The final rule is HUDs Rule. And HUDs Rule states that electrons can occupy orbitals of the same energy in a way that makes the number of electrons with the same spin direction as large as possible. So let's look at what that means, because that sounds like a whole lot. So 3 electrons would occupy 3 orbitals of equal energy as follows. So for example, the 2p orbital, or any p orbital, has 3 orbitals. The 2p sublevel has 3 orbitals. And if we have 3 electrons that we need to fill, we fill 1, 2, 3. So we have to space them out since we're within the same energy level. And since we're in the same energy level, they got to get spaced out first before we pair them up. So we do not fill it like this. 1, 2, 3. This is no bueno. We do not fill this in this way. So electrons then occupy each orbital so that their spins are paired with the first electron in the orbital. So for example, let's say we needed to put 5 electrons in the 2p. So here's my 2p orbitals. We fill 1, 2, 3, then we go back 4, 5. So fill all the orbitals first in that energy level, then go back and start pairing them with the opposite spin. So there is a shorthand method for showing electron configurations. So first we'll show it with the energy diagram. So for hydrogen, we just have 1 electron. So we need to obey all our rules. So the Aufbau Principle says that we start at the bottom. So we just pair our 1 electron alone, and it's in the 1s orbital. So our electron configuration, or our shorthand method, looks like this. We first name the orbital that we entered, so 1s, and then using a superscript, we say how many electrons there are. So 1s1. Now let's look at oxygen. So here we're going to need to think about the Aufbau Principle, the Pauli exclusion principle, and HUDs Rule. So Aufbau Principle says we start at the bottom. So we need to fill 8 electrons. So 1, then come back and pair it. 2, go to the next energy level. 3, we need to pair it. 4, jump to the next higher energy level. 5, 6, 7, then we go back. 8. So the way we filled that has to be the way that you fill these. You have to follow those 3 rules. So let's turn this into an electron configuration. So we start at the bottom. First we ran into 1s2. Then we have 2s2. Then lastly 2p4. Notice that we needed to use 8 electrons, and if you add up our superscripts, 2 plus 2 plus 4, we get our 8 electrons. So your superscripts should always add up to the number of electrons for that element. So correct electron configurations through vanadium, which is atomic number 23, can be drawn by following the Aufbau diagram. However, once you go past there, if you continue, you would assign chromium and copper the following incorrect configurations. So chromium has 24 electrons and copper has 29. So if you fill it following the Aufbau principle, you fill up through the 3p, then we go to 4s, then to 3d. However, these orbitals here, so 3d, d has 5, so we have 4 here. Elements do not like having empty orbitals if they don't have to. So the correct configurations are these that follow. So notice how here we had 4s2s and 3d4, 3d9. And here we have 4s1, 3d5, 4s1, 3d10. So what we did was we had our 4s electrons. So to start, we had the incorrect format. But, like I said, they don't like to have empty orbitals, so what we do is we take this electron, because it will suit us better here. Half-filled electrons are half-filled orbitals are much happier than empty orbitals. Same thing happens with copper, because you have 3d9. So as we fill these, 4, 5, 6, 7, 8, 9. So we take the electron that would go to the 4s and we add it here. This only occurs for the groups or the columns that are underneath copper and chromium. So these arrangements give chromium a half-filled D sublevel and copper a filled D sublevel, and that's what they prefer. So some actual electron configurations differ from those assigned using the Aufbau principle, because although half-filled sublevels are not as stable as filled sublevels, they are more stable than some other configurations. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, the resources CD, and pearsonchem.com. Have a great day.